So to start us off, I'm going to show a little snippet of what the AI looks like, quote unquote, fully trained here. So you can see briefly there, like bit by bit, here's all of the actions the model can take and stuff like that. And you can see it executes really fast. So that was 10 actions in a row. And I will get into what this all means in a little bit, but you can see it has some sort of memory, it has some sort of subtask. You can see the mouse coordinates of where it's moving right here and what it's trying to do. And so when we get into the actual battle, this is also what it looks like. And that was its actions. And ideally something that would happen here is that you would expect the cursor to go and click one of these things, and then it actually will watch the battle. But that's not what happened here. For many reasons. The biggest one is that I have like very little training data for this, but I will get into all that soon. But this is what this robot AI looks like in action for Toontown. But what is this? What's going on? What is this robot AI I'm referring to? I will get into that right now. So what I'm referring to as the robot AI here is a Toontown vision language action model. Now, vision language action models have been used for a couple of years now in robotics to have them perform tasks like this, of like opening stuff, moving things, and doing other random tasks like that. And the reason I created this Toontown vision language action model is because I wanted to understand what these robot models were doing, but in a much more simple environment for video games that would hopefully need less data, less, intense, I guess, model sizes and other things like that. My goal was really just to recreate, to the best of my ability, some of these vision language action models, understand their machinery, understand how they work internally, how they generate actions based off of the observations that they see. Like this is a single frame, so if it got this frame, what will be like the actions generated from this frame, and what all goes into that. My scope here was I really wanted to make this model good at battles. I wanted to collect enough data as to where I could actually kind of go tit for tat here with like a cog or something. If you know Toontown, that would just be like defeating this, I think, level 1 or level 2 cog in a battle. And I didn't end up accomplishing that goal for a couple different reasons, but I'll get into that a little bit later. But as for understanding the machinery, I think I actually did that pretty well, and I do feel like I know a ton about vision language action models now, and that I know the machinery of how it takes in images and generate actions pretty well, especially based off of this Pi.7 model, which I created this Toontown vision language action model based off of. So I say it's very, very heavily inspired by this 5.7 model, and that's true. I basically tried to copy everything in this model almost like bar for bar, except at a smaller scale, and I did make some modifications that I'll get into in a bit. But first, I kind of want to go over this model and just explain how this ends up generating actions that look like this for Toontown. So I'm going to go through that bit by bit, and we'll get started with that. So for a better explanation of how these vision language action models work, especially inspired by this physical intelligence model, and I'm using the kind of physical intelligence models as the basis of my understanding because I think they're the most interesting in this space. I think they're probably one of the industry leaders, and I've been always really impressed with their work. So that's why I wanted to learn from them and kind of follow what they did. And that's what I'm going to be explaining today. There's other ways to do vision language action models. There's quite a bit of ways. There's other kind of components you can add and other things you can add like that, but I'm going to explain the vision language action model that I made, not all of the vision language action models. But if you're interested in this space of how robot arms take in images and output actions, hopefully this will provide a good basis for that. But also understand that this isn't everything in that space. But at its most basic, this is what happens in a vision language action model. So vision, language, and action. For vision language, they always base that off of a vision language model. And then what they do is they take a vision language model and just add on a action expert. Now, I'm not going to get too gory into the details here, but a vision language model you can think of as a normal kind of ChatGPT style thing that can take in images and like output text. This will take in images, output text, but it'll also output actions. And then the actions go through what they call action expert and then get decoded into continuous actions. That happens through a process called flow matching, and it's pretty interesting, but I'm not going to get into that here. I just understand that the broad point of vision language action models is that it takes in some images, as you can see here, some language prompt, high-level prompt will just like clean the bedroom, so you get images of it starting to clean some bedroom, or like, I guess, video of it messing with a bed with the high-level task of clean the bedroom, and then it outputs some action. How physical intelligence does it is they have the AI, what they call backbone here, and they have it with the images in the prompt, they have it spit out a subtask. And that subtask is kind of like breaking things down step by step. So like if you clean a bedroom, you don't think, oh, I just clean a bedroom. You say, okay, I first go and say like fold some t-shirts or, put a blanket over the bed, pick up toys off the ground, whatever. But those are subtasks. They're like bullet point instructions for how you would, coherently all together clean up a bedroom. And they use that subtask along with both the high-level prompt and the images to actually generate the action. And now something interesting here that I had to implement in the Toontown VLA that they do in their later vision language action models, which they didn't put here, but it's in one of their earlier papers, and you can kind of see it here, is that they break this up. So when the action expert trains, it does not have its training gradients flow into the vision language model, and it doesn't let the vision language model training gradients flow into the action expert. To put that more simply, I would say like when you're training a model, you're training it to reduce errors in its training set. So like if it sees this and the subtask, it should first output this and then generate these actions. And if it does that wrong, well, then you send the errors back to the model so that it can update and do it right next time. And all that is saying is that they update these differently. So the pre-trained VLA gets different, like its update is not connected to the action expert's update. And that is because when they do this in later models, but they have a discrete form of their actions, and this discrete form of their actions is put into the VLA as a target as well. So they want to predict the discrete form of the actions, and that allows for this vision language model backbone to be able to make representations that can predict actions roughly. And the discrete form of actions are pretty good, so you can hope that the vision language model representations it's making to predict these discrete form of actions will be helpful for the action expert to produce its continuous actions from. But this breaking up of the gradients just allows them to keep it clean. So like information leakage from predicting the discrete actions won't go and leak over to helping predict the continuous actions, and vice versa. So that's something in their 5.7 paper called knowledge insulation. They've used it before, but I used it in my Toontown VLA as well. Another thing that they added in their paper for the 5.7 VLA that I mostly recreated was memory. So this was pretty interesting and actually pretty complicated for me. The text memory wasn't too bad because there's when you are giving this high level prompt, like clean the bedroom and breaking it into subtasks, the text memory just basically combines the subtasks. So like if you have the task of clean the bedroom, you would say, okay, I picked up the toys and now I'm going to start like folding the bed sheets. And that would be the text memory. So like it's just like chaining subtasks and like a coherent framing, kind of the way that you would, I don't know, like describe your actions if you were picking up or cleaning the bedroom. Visual memory was a bit different, a bit trickier to implement. So what visual memory did was it took this pre-trained vision language model backbone, and what they did with this was when you have vision language models, there's a vision part of the model and a language part of the model. And the vision part of the model, as you might have guessed, is what processes the images. So like it'll take the images and then get them into a place where they can be essentially tokenized by patching them and put them with all of the text tokens. So eventually you get one long string of tokens, and the vision part of that is what gets those images into those tokens. What they did was pretty interesting, was that they modified the images, the like vision part of that model, to essentially be a video model. So what they did was, and yeah, down here you can kind of see. So what usually happens in the vision part of the models is something called spatial attention. And that's what you can kind of see with my cursor right now, is that these patches of these images attend to other patches of the images. They did a actually really cool graphic here. And this happens over like, for the vision model I used, there was 12 layers. So it does spatial attention for 12 layers. So like at one layer, it'll do spatial attention, and then it'll do all its other things, and then do spatial attention again. So it'll continuously like look over these patches to try to effectively understand what's happening in the images spatially. And what they added to add visual memory to these models is that they took these frames, which they considered these frames temporally. So like this, as they say, is 2 seconds ago, 1 second ago, and then current. And then every fourth layer, so if you have like 12 layers, that usually processes like each image in these, which usually processes each of these images like separately, spatially, for each of the 12 layers. What they did was every fourth layer, they process them temporally. And so here's another cool graphic showing this, but you can see like this patch now, instead of attending to the other patches, does attend to the patches across time. And I get, okay, this graphic is a little confusing here because you can still see the arrows go to the other patches in the images that I'm focusing on. And that was a little bit of a learning curve. But essentially what happens is first it does temporal. So like the A goes to the other A's in these images. And then after the temporal attention, then it does patch-wise attention. So after it has gotten the information from all the A's, essentially compressed into one of these A's, then it takes all of the, then it does the spatial attention. So it first compresses temporally, so all of the A's go to one A, and then spatially. So you can think of it, it does this for every single one. So all the B's get spaced or temporally compressed into this B, and then all the patches attend to each other spatially like normal. And then at the end, they discard the other two images they use. So they don't care about 2 seconds ago or 1 second ago. They only care about the current one. And that's because at the end of all these layers, they should, as they say here, have a compact representation of its current frame and its previous frames because they temporally compacted them here using the temporal attention. And this might sound like completely insane. I thought it was completely insane. You can see my code for this if you want to. You can go to my training notebooks here, and then for the low-level training, and then just scroll down, and it will be in somewhere around here. So like process memory, and then so first temporal, then just spatial, and then you're gonna have to wrestle with that for a while. This paper built off of another paper, whose name I'm forgetting, but it has the equations, it has the other things. This was probably the part of the project I really had to wrestle with the most. This part was quite mentally tricky for me, but I do think it's super cool and very interesting that you can modify the vision part of the transformer into something that can process videos, which you can think of a video as multiple frames here, just by changing the code around a little bit. And again, you can see that right here with my process memory functions and stuff like that in the training notebooks. But yeah, if you don't understand that, but you want to, I'd highly recommend you read this MEM paper and its previous papers that it was building on, because they'll help you figure that out. But again, very cool. So it compresses it all into one frame, and this frame is what gets processed into tokens, and then those tokens get combined with the language to give the sort of prompt that goes in to generate the actions from. So all that, everything there is all to help generate the actions. As always, everything here, all of the machinery that you're going to see here, all of that is to just give representations for the action expert. That's what everything does. And what they added on to this 5.7 model, which is their most recent vision language action model, is subgoal images. And these are images that are a couple seconds into the future. And what they are supposed to do is supposed to give sort of like a future grounding for where the robot is supposed to move. And so I tried to recreate something like this. And you can see down here they call it a world model. A world model essentially is supposed to take the current, I guess, aspects of the world in whatever sense you want to define it, and then be able to predict future states of that world. And so I guess this technically fits the definition, but like you take a frame and then the world model would generate what that frame is supposed to look like a couple seconds in the future. And so I did this by copying them, but I didn't use their world model. They used Bagel. I used what they based their research on, which was instruct pix to pix. And so I'll give a little example here, but you can kind of see, so this would be one frame, and then the world model would need to predict this frame. So like you could see in the past there was no cursor, but now there is a cursor and timer's moved. And so this would be a couple seconds into the future. It would say, okay, if you're right here, you need to be right here. And this provides the grounding for, again, actions, because everything is about providing representations for actions of what kind of it would need to do in the future. And then as they describe in the 5.7 paper, I don't have it pulled up or marked, and what they describe in the 5.7 paper is that this provides a sort of inverse dynamic sort of thing where they have the states they want to be in, and then they just have to get to that state, if you know anything about kind of robotics and dynamics and stuff like that. Another thing that they added in this 5.7 model is metadata. And so metadata is where another thing they have in this 5.7 model is metadata. Metadata is just for each episode, and you can think of like something like this as an episode where it's trying to chop a cucumber. So like, let's say it chops one cucumber and it does it really well and it does it really fast. You would put, oh man, that's high quality. That's a 5. And they use their scale of 1 to 5 for quality. So it's like, man, that's a 5. That's a great. You really chopped that thing up and it was so fast. So let's say you did it in like, I don't know, 200 seconds. And then it tries to chop another cucumber and it's just awful about it. So it's like, oh man, you really sucked. We're going to put that as a quality of 1. And you like did it horribly slow, so that's even worse. So we're gonna put that speed as like, I don't know, you did it in 500 seconds. So you really sucked that time. Now, this is a new addition to vision language action models that I've really seen. Usually for these, because they're trained on imitation learning, you want them to have like perfect quality demonstration. So like all of these need to be perfect. But metadata allows essentially for you to use like really shitty quality demonstrations. And it's great that you can, because like not all demonstrations are going to be good. So by having this metadata, you're like able to use like bad quality demonstrations to get better results. And how that works is classifier free guidance. So during model training, what they do is they randomly like drop out metadata and quality so that the model ideally learns just like what the distributions of with the quality and the speed and without the quality and the speed. They also drop out sub-goal images, and sometimes if they have sub-goal images, they drop out the subtask predicted. They added quite a, I wouldn't say a lot of dropout. I mean, all of these are kind of low quantity, but they did add some dropout, and all of that is to allow for classifier-free guidance. It's mainly used in image generation, but with classifier-free guidance, what you can do is, I'm going to try to roughly draw how classifier-free guidance works. So like, if you have, this is your distribution of, say, like bad, like metadata. So like it had like 1-star quality and it took forever, and you don't want that. And you have this distribution of good, you know, sort of what you've been trained on. So like if you train on the bad stuff, so like sub-goal images for a bad run, language instructions for a bad episode, low quality, low speed, the model is essentially learning a distribution over the frames and languages and sub-goal images and episode metadata of the bad stuff. And then if you have a good episode in training, then the model's learning a distribution over the good frames, the good prompt, the good language instructions, the good sub-goal images, and the good episode metadata of the good distribution. And so what classifier-free guidance does is, if you drop out this episode metadata, then it just learns like kind of like the basic distribution like this. You know, it kind of learns everything. Or like, I guess I can't rely on the episode metadata to tell what distribution it is. So it's kind of like a more, I guess, I don't know, ambiguous distribution. So what you can do in inference is take this good distribution and take this regular kind of unknown distribution, and then take good minus the regular, and this will give you a direction, and the direction will then be amplified in good. So you take then the reg distribution times the amplified direction of amplified in a good way, and that's classifier-free guidance, and that will hopefully give you, once again, the good distribution. I hope I hope that makes some type of sense, but that's classifier-free guidance. You're essentially, you have this ambiguous distribution, and then you have the good condition distribution. You want to take the good one, subtract the regular, which is hopefully subtracting the bad and kind of mediocre to really amplify the good, and then times the regular distribution, which you would get from running the model in inference conditioned on like its current observation, its current language subtask, and the predicted subgoal. And because in inference it's a subgoal image predicted by the world model, there's no ground truth future. And then you'd want to push that as far as you can, really push that into the good category. So you wouldn't want it to be bad anymore. So say like get rid of that bad distribution. You want this to be best possible distribution. And that's what classifier-free guidance is doing. It's guiding it into the best possible place it could be, and it can only do that if it understands what's mediocre and bad, and that's what you get if you include bad and good metadata. So very cool that they added that. But obviously, I think it makes training harder because you have to add in metadata, you have to label a bunch of these examples of metadata, and then, I mean, classifier-free guidance training is kind of free because you can, of course, just drop this stuff out, but data labeling takes forever and a half, and so you're still adding another component on that can take up a lot of time. Adding in a world model takes up a lot of time, because then you have to, of course, get the future images and train the model and everything. And then this is even before getting into the inference masks, which I'll actually show you about. Sorry. All right, so this is what happens during inference, and you can ignore this stuff over here. But they have their metadata with classifier-free guidance, and they take their images with memory, and there's the negative prompt, and there's the positive prompt, and of course that's what they subtract positive from negative to get the good direction, and then multiply that with a regular pass through the model to get the best possible version of it. But you could see the building out this this mask here. This is one mask. So what they did was they packed everything into one mask. So they allowed the vision language action model backbone here to be able to handle both images as memory, then positive text and positive flow actions, and negative text and negative flow actions. And they packed it all into one prompt. And of course you have to make a model designed to do that. And so like this also gets pretty complicated because you're making, I don't know if they made the architecture with this in mind or if it was like a late addition that they added back. I don't know where the subgoal images are here. It's never talked about. This is regular training with the subgoal images. So you need a mask, you need an auto-regressive text mask, you need the goal images regular, and then you need to have auto-regressive action tokens. So this is the vision language model reps that I talked about way before. That is their version of actions. So they're predicting the auto-regressive actions for the vision language model, and then there's the flow actions, and the flow actions and the regular vision language model actions don't interact. So there's like this little chunk here, and so like if you're building out this model, which I did, you have to make this giant mask. And if you go to my code, you can find this somewhere. Yeah, well, this is what I called it. You can probably find a better name for it, but I made this insane mask. And it's even worse when you go to, this is the world model. So this is what they did in inference for the world model. And you can read through this if you want. I mean, this mainly depends on the world model they use, which is Bagel, for why it's so complicated and needs to use both a vision transformer and a variational autoencoder. But you got to build out these masks, and it just makes everything more complicated. So, like, when I started this project, I mean, I was, I guess a little ignorant, I guess you could say, about how intense this would be. And this is before even like getting into collecting training data and labeling the training data that allows for all of these things, which again I did. You can go into environment handling and data set labeling, and there's this full VLA labeling tool that I helped make. Part of it is vibe coded. I didn't mind vibe coding some of like this like pie plot stuff because I don't really care about that too much. The model, that's all me. The labeling, yeah, that's a little bit vibe coded. But I made sure it worked. I overlooked it all. I guess I don't know. Is it vibe coding if you overlook the code after to make sure it's done, or is that just pair programming with an AI? I don't know. That probably doesn't matter. But yes, that is every component of this 5.7 model, and every component is here in my VLA style Toontown model. So, I mean, there is some differences. So, like, and I go through a lot of them here. I didn't use their world model. I used instruct pix to pix to do the future image editing, and I didn't use their giant mask because instruct pix to pix doesn't need that. Every part of this model is undertrained because collecting the data it takes forever, and I just kind of wanted to understand the components of the model rather than try to recreate something that is just like super amazing. Like, I understand the true scope and gravity of the process when I finally was getting everything sort of completed. I was like, oh man, like if I actually did this, this would take a really, really long time. Like, I understand why these companies need to be so big because they have to be. They have to be to do these kind of engineering tasks and to label all this data and collect all this data. It's an incredible amount of work. But I guess to sum this part up, just know that I did my best to recreate all of these components, and all of them are there spiritually, if not 100% perfect to the actual model. But all of them are there spiritually, and you can read about all of the differences down here of where I diverged from the paper and where I made my own assumptions. So, like, I didn't know during their training because, like, there's observational history, and so, like, I probabilistically made it so, like, 5% had no history frames, 10% of, like, the training batches had one, and then 85% had two, so, like, that'd be 3 frames with 2, like, history frames, as you can kind of see here. And so I made those assumptions clear and tried to do my best. I'm just going to go over what I got from this project. So I got a huge amount of implementation experience. I literally had to tear apart everything from a vision language model backbone. I mean, I went through the text component, like all the language handling parts, all the vision handling parts, because I had to make the mem or a memory, function. I had to wire up all of the multi-head attention, or like each attention stream. I had to get the representations from the vision language model and the action model, and then combine them together into this other like new attention stream or new attention calculation where the action expert can attend to the language model, vision language model, and then I had to add the crazy masks so that they can't like send their gradients back through each other. And then I even created a path for vision language model only and then action only, so that during inference time, I could pre-compute all of the vision language model stuff and then run the flow matching of actions based off top of that. So a ton of, I think, really solid engineering experience, you know, tearing apart models, or at least one model, and kind of shaping it into the way I wanted it. And then especially following papers and reading them and understanding what to look for and things like that. So that was really cool. I implemented like 4 to 6 different papers during this project, and one of them was even flow matching. So I didn't know flow matching very well before this, but I had to learn it to make sure this all worked, and that was really, really interesting. I think flow matching is super cool. I mean, I knew diffusion before, but you know, flow matching is it's surprisingly simpler and better big brother, and that was really fun to learn. I learned a lot about debugging because, of course, when you're making something this huge, you're going to run into some really weird bugs. And some of that is like knowing, I guess, what to look for when things aren't training correctly or not having inference correctly. So, like, one of the bugs I hit at the start of this project was it would train. So, I always do an overfit calculation so that I can know, like, it can really overfit one data point. And if it can do that, it can take in a big batch and start to really learn. But I had it overfit one data point, but then when I did inference on it, it would produce garbage. And I was like, why is that happening? So I had to essentially like dig through this this inference stream and find out where it was failing and then correct that. So I learned just a lot of ways to look at what bugs are happening, why they might be happening. It ended up being a problem with like the residual path and one of these action calculations. And it was just, I mean, it was a lot, but I learned a lot from it. I also learned how to run stuff on the cloud. I trained on RunPod. So you can see down here how much money I was spending to do these little training runs. And I know this isn't anything like, people spent way more on their AI projects, but money is money. And so like a good chunk of this was first debugging and then actually doing the big runs. And you can see the big runs cost me like $10 on almost $10 on August 12th. And those were the final runs. And like the low level model especially really required like a huge model, like a huge graphics card with a lot of VRAM just to get 2 or so, like a batch size of 2, because there's so many images in these things and images take up so much space. And so I really had to learn like calculating VRAM and then the cost of like how much it would take to train one of these things and stuff like that. And it was like, man, there's no wonder these like physical intelligence got like 5 million or like $500 million in like venture capitalism money. Is like, yeah, I mean, if they they would need to probably get through the next training run. It's no wonder they get all this money, because that's how much this thing costs. It's insane. Because not only like, especially them, when they're experimenting with this stuff, they have to create a bunch of different models like this and train them and test them and like look at their efficiency versus their past models and stuff like that. So like this very quickly becomes easily $1 million, like hundreds of thousands and stuff like that. Just from like training and setting it up and the people and infrastructure cost alone. So I got a glimpse into that. My little $10 here was a glimpse into that, but that was also really interesting. Another thing that I learned about during this project was cloud inference. So like hosting your model on the cloud and having it execute like requests and then send data back from the cloud and stuff like that. And that was also interesting. I used Modal. Modal Physical Intelligence also uses Modal. I didn't know that when I started using Modal, but that was a fun little surprise, because that means, hey, I kind of use what they used. Of course, theirs is obviously a lot more complicated and a lot better set up. Mine was just kind of like a little bit more thrown in there as I was figuring stuff out. But I learned kind of how to set that up, how to look at the logs and stuff like that, and all of the other things. And yeah, you can kind of see here the predictions. So like the predict method was from my model that handled everything. So like connected the world model, the low level model, and the high level model. And you can see route through post, the startup times, the execution time in seconds after it started up. The failure statuses, I think, were just me interrupting and playing with things. But yeah, I mean, that was also really interesting to see how this stuff actually takes, how long your model actually takes to run in the wild, the latency time of how long stuff takes to execute. And that's one place where I really diverged from the model, was trying to optimize it for execution. Like the physical intelligence people used async for their world model and their action generation model, and I didn't do that. I just ran it linearly in a chain. And you can find my code for inference everything here, and it includes the modal setup if you wanted to use the VLA to set up your modal stuff. But if we scroll down here, you can kind of see that I just had it generate the subtask from the high policy model, or like the high level model, which you can see here. So I'm just following literally pretty much this inference time thing of get the task, generate the subtask, send the subtask through the world model to get the subgoal image, throw all that into the prompt, and then generate actions from it. So that's what's happening here. Get the subtask, throw it all into the world model, get the actions from it, and then send the actions back. They do async so that none of this is blocking the the low level action generation, and that greatly reduces their latency time for action generation. Also, that crazy tree structure here for classifier free guidance means they don't have to run the model twice, which my model does have to run twice because I didn't build it out like this. And that also introduced a lot of latency, so that's where all of this huge execution time comes from. The physical intelligence team tries to execute in less than a second, and I'm at 9 seconds. So you can see how much some of those optimizations really matter. But again, the spirit of the model is here, just not optimized. And again, I'm trying to go for the spirit of the model because I really wanted to understand these vision language action models. And I feel like I really have. I feel like I really got insight into these models. What the research looks like, what they want to focus on, what their goals are, and why they do the things that they do. And there's so much I learned that I'm probably forgetting here because it's just become so second nature over the course of this project that I don't even feel the remember to point it out, because it's oh yeah, of course I know that. But I believe I really did learn a lot, and hopefully if you actually read through all of my code here, you get that impression as well. I know this is a recreation. I know this is not original research, but I do think it'd be hard to say that I didn't truly grapple with all that went into what goes into training a vision language action model, because I really did have to fight through every part of that implementation to get to a point where my model, when severely undertrained, can execute from the cloud in the Toontown environment as it's running. So it may have not met my goal of becoming a great vision language action model. It definitely can't compete battles, but I'm still happy with all of that I've learned. You know, I still feel like I did truly understand it and truly understood what's going on with vision language action models and how they work, at least in the physical intelligence case. And again, I believe that they are at least at the forefront of this research. So I'm hoping that they serve as a solid proxy to understanding most of the or vision language action model research. And I am cool with that. That being said, this deep understanding of vision language action models does lead me to understand where I believe the limitations of these models are. It takes so much data to collect. The training costs are incredibly high. The inference costs are pretty high. Adding in all of these subcomponents to get better representations for the prompt to generate actions from seems, I mean, as impressive as it is, it also adds so much complexity to, again, more training costs and then inference costs and then training the world model, training the high level policy model, and then training the actual action generation model. And you have to train these in a way where all three of these are properly aligned or everything just flies off the rails. I mean, think of a high level policy model that generates some garbage subtask, like if you say, oh, clean the bedroom, and it first decides, okay, pick up a knife from the kitchen, it's like, well, then your world model is going to generate a sub-goal garbage image, and then the prompt's not going to know what to do with that, so the actions are going to be completely off. You have to align all these three things during training, and if you keep adding on more and more and more and more and more, I don't know how sustainable that's going to be, but that's the whole point of the research. And so, as I know more and as I'm impressed with it, I also feel like I get a really much more understanding of the downsides of this sort of idea of generate representations, which the action expert can use. On a more personal note with this recreation, I did a lot of, I made some mistakes, definitely. So I kind of want to go through those and try to think about what can I do better next time. So one of those mistakes I was talking about was I was unable to kind of do this tree packed structure of classifier free guidance. And that's because when I built this Pi point 7 inspired model, I built it kind of ground up. So I started with the vision language action model that had knowledge installation, and then I built the high policy model, and then I built the world model, and then I added on the metadata. But doing that kind of like from A to Z, I didn't coherently look at the whole picture here and realize that if I was building it the way I did, then I needed to build it with this in mind. So this would be Z, and this type of structure needed a different A. It needed me to build my vision language action model in a certain way to be able to accommodate that. So I didn't really get full coherence with that. Like that's something that I want to try better for next time is, I guess, having all of the parts in place, or like being able to look at the, like, especially if I'm going to build it out like 1, 2, 3, 4, making sure that the fifth part of that doesn't end up requiring part 1 to be completely redesigned, because that was kind of a bummer when I got there. For memory, and I noted this here, but when I built this out, I was hyper focused on it. I really focused on making sure that the video frames got arranged and dealt with such a way that it was accurate. It was good, and I'm happy with that. I think I did that well, and I think it works. The problem with that is that this also requires that the proprioception, which is just the model's state of being, also have history. So it needed for each video or each frame of input, you would want proprioception to have one 2, or 3, depending on how many frames of input you had. I got so focused on the video part of it that I completely forgot the proprioception part of it. So it only takes in one proprioceptive state and doesn't dynamically expand with a number of history images. And that's just because I got too focused on the memory part of it. And I only remembered this right as I was doing the finishing touches on cloud inference. So I'm like, hey, wait a second, shouldn't I be passing in more proprioceptive states? And then I realized that I completely forgot about that. So, whoops. Definitely another thing for next time of just if you're focusing on a specific part of one paper, of a recreation, just double check it at the end to make sure that you're not missing anything. Like, I don't know, I was pretty proud of this, and I was so proud of it that I moved on when it was done, and I should have looked it over more. Another thing that I would like to work on is some of this code is kind of clunky, as I would describe it. You know, like there's some things that I definitely think could be optimized, and I think that's always a problem for programmers when they look through their code. It's like, oh, that could be done better. That could be done better. And I definitely feel that way through this. And there's some hard-coded stuff here, you know, that maybe could go in like config files and other things like that. So maybe just next time I want to be a little bit cleaner about things and make sure that, you know, a lot of these sort of like stuff where you define like variables and things like that are a little bit more easier to understand. I mean, this works, but it could be cleaner. It could be cleaner, and I'll definitely try to get better at that. Oh, also, I had to figure out batch samplers because creating the the data loaders for this low level training, low policy training, you know, low level policy training, it was actually quite a kind of complicated because you have so many different things, you know. I mean, you got all of these going into batches, and you got to train in batches for efficiency. So, yeah, I had to learn about batch samplers and collate functions for data loaders, and that was pretty interesting as well. But nah, that's a little tangent. And I guess the last thing that really stuck out to me is maybe I could get better at was I did talk about this, but I made some, you know, assumptions based off of the papers here, and I don't know. I went back and forth on should I reach out to the authors about this? Like, should I email them, like asking them, like, you know, what did they use for the probability of drop of like history frames during batches? Like, did they even do that? And then there's especially one for like memory where they like they had in the memory paper they had this equation on equation 3, and here I'll pull it up. So this is what I was talking about with the temporal and then spatial attention. So this is what I think is describing temporal every fourth layer, and then spatial like after that temporal attention every fourth layer in the video memory encoding. But as you can see here, well, I won't make you read through all this, but roughly the way that this is defined, it makes it seem like they do spatial temporal attention and then spatial spatial attention on top of that spatial temporal attention, and I think this should just be temporal. And I didn't know if I should reach out to the authors about that. I'm still not confident in doing that because I don't want to sound like annoying. So I don't know. I don't know where I land on that. But I figured I'd mention it here because I think I could get better about just, you know, I don't think it's wrong to reach out and try to get questions clarified. But I don't know. It's still a little nerve wracking because I'm self taught. And I don't know if that's like, you know, something you do in the industry. But it was just something I was thinking about. So hopefully you understand what this project is. It's a vision language action model inspired by the physical intelligence team's vision language action model, using all of their components, but, you know, at a lower scale and sometimes not exactly their components, but spiritually it's all there, at least to me. And this was to understand vision language action models, to deeply understand how they work in both the papers, so what they're trying to do to get them to work efficiently, and then engineering wise, how they work, at the ground level. It's not perfect. There's definitely a lot I can improve, but I've definitely learned a lot. And, it's been a very enlightening experience for me because I figured vision language action models were the way forward for, really expressive AI systems that can do stuff in the real world and, work well at doing tasks and things like that. And I do think they have a lot of potential. I do think the research is very good, but I can see a lot of the downsides that greatly concern me now, especially with data collection and training these models and inference with them and other things like that. So I don't know. I think I'm gonna start looking into maybe some other research directions for some more expressive neural network architectures that can maybe work a little bit more without having to manually design this high level policy and then the world model and then the vision language action model, because all of this just takes so much effort, and it's hard for me to think of like this tool coming to fruition where all of that is required, but maybe it is, and I don't know. I'll definitely keep an eye on it. I will always keep up to date to the best of my ability with vision language action model research. I think it's super cool. I like what they're doing, but I also think it can be improved, and I want to see how I can do that and get involved in some research and engineering projects. And if you made it this far, thank you for watching, truly. I hope this wasn't the most insane thing you've ever heard, and I hope some of these explanations maybe even made sense. If you are in academia or like engineering projects or anything like that, and you think I might be a good fit for that, let me know, because I really do want to get involved more in this stuff and I do like working on it. So if you have a cool project, please feel free to reach out. But this is my Toontown VLA. I hope you found it interesting. If you want the code, it's all open source. I'll post a link in the description. So, please try it out. Generate your own data if you want. This is I tried to make it pretty environment agnostic. So you can definitely, I think, try this out for any environment you want. You can try it for any games you want. Again, inference might be slow, but, definitely parts you can improve here. But I just wanted to kind of do this retrospective on the project where I explained what the VLA was and how it worked and kind of what my issues were of recreating it and then where I think VLAs are. And hopefully I reasonably managed to do all that. So thanks again for watching, and I hope you all have a great day.